Hi everyone, welcome to this lecture on 2D chromaticity histograms. 2D chromaticity histograms are a way of representing and understanding colors in an image, in varying to the amount of illumination in an image. So we'll walk through why do we need chromaticity, the math behind it, explaining the building of 2D histograms, its key properties, its applications. We'll walk through a small example and the limitations of this approach. So why do we need 2D chromaticity histograms? Why not RGB values? So the thing is, for RGB values, the same object, same surface will have different pixel values under different brightness. So a green leaf under bright sun might have RGB values of 120, 290, but the same leaf in shade would be something like have pixel values like 40, 16, and 30. Your model, which might be trained to pick pixel values in the latter case, might not be able to identify the leaf in other in dimmer illumination settings. So these two pixel values are very different, but they belong to the same object. So we want our model to be able to recognize the same object irrespective of the illumination available. So, for example, we could have a red apple, and in bright light, it could be 220, 60, and 40 pixel values. Our model which is trained to pick apples in this bright light, when the light is not so bright, or maybe we have a window near a big window and way more light than it was trained on. Now, the model might fail, it might get confused, it might not be able to identify the apple accurately since the pixel values, RGB values, have changed a lot. So what do we do is we normalize by the illumination. So we take the sum of the pixel values across all the three channels, and we divide every channel by the total amount of intensity. So we kind of normalize. We have a normalized R value, which is the red pixel value amount of red in that pixel divided by total amount of intensity in that pixel. Similarly, a normalized green value and a blue value. Since they all amount to one, the blue is anyways 1 minus r plus g, so it's redundant and we don't really need it for analysis. So we'll just create a 2D histogram of r and g, and that's enough for chromaticity. So in this 2D histogram, okay, so for illumination invariance, so whether it's dim light or bright light, so we have two a same image in dim and bright lights, and when we normalize it, it has similar R and G values for the same object. So it's like same chromaticity when the intensity is removed. So to build a histogram, what we do is for every pixel, we compute the RNG values. Then we quantize these RNG values into n number of bins. We could decide an arbitrary n value. How many bins do we want? We could choose to have larger number of bins for a better analysis. And then we increment the count wherever we get the same. For each RNG value, we increment the count in that cell and in the 2D histogram, and then we can normalize by the total pixel count, and then we visualize it as a 2D heat map, and it's a right angle triangle, and the clusters, each cluster represent one unique kind of object, uh, because each unique object would have similar RNG values. Each unique object would have clusters of specific RNG that are very similar. So each cluster in this histogram is one different object. So yeah, that's a heat map. Peak cluster. Each hot region is a different real world material, and the axis, x-axis is the R channel, vertical is the G channel. Each axis runs from 0 to 1, and the constraint is R plus G has to be less than equal to 1, so it's a triangle. Um, and the near achromatic pixels like gray, white, black, so which are like similar values, they are around the center, which is R, G, and B are approximately it's 0.33. So applications are skin or face detection, in object tracking. For example, we have a video and maybe the lighting changes or the camera angle changes, and we want to still be able to recognize that object consistently. So we will use a 2D histogram because when we normalize by the intensity values, our 2D chromaticity histograms, heat maps, they remain the same. So we can use it for object or region tracking. We can use it for scene classification. Um, Irrespective of indoor or outdoor scenes, the chromaticity would remain the same. And we could use it for image retrieval, for example, to find visually similar images. We'll walk through one example here, which is we have this image of apples, and so see, these are apples in a garden. So for these red apples, they form one cluster. We see one heat map here, yellow heat map towards the red, which is a larger heat map. So these are the red apples. The green leaves, they represent another cluster, another heat map of yellow points, yellow pix. So this is our one cluster leaves, another cluster of apples, and this pinkish purplish tail you see, which goes towards the center. These are essentially the mathematical record of objects losing their vibrant colors as they fade into shadows. So these are neutral tails. So this comes from the dichromatic color theory, where we say that the amount of illumination from an object, the amount of light in an object, is the sum of its body reflection and the source reflection. So the body reflection forms clusters, the different objects, while the source reflection forms a neutral tail like this. The tail goes towards the center neutral colors. Uh, yeah, that's for the applications. And let's go ahead. The limitations is when we have very dark pixels, which are close to zero, chromaticity will be undefined. And when we have specular highlights, for example, when we have bright white highlights, so the chromaticity would shift towards neutral, and we would have difficulty making clusters. Similarly, when we have very bright colors, strong colored light changes, it changes it can change chromaticity even if the surface is the same, and we will have loss of one-dimensional information because all intensities map to one point here in a histogram, so we can't reconstruct original color. Also in this, it's worth noting that even if we brighten the image or we darken the image, our histogram, our heat map essentially remains the same, which is what we talk about, why we talk about illumination invariance in 2D chromaticity histogram. So this basically kind of remains the same. So it's invariant to illuminate the amount of illumination, the amount of light available in the image. That's what we say. And that's the biggest advantage of using a true 2D chromaticity histogram. The amount of light won't affect our clusters, and we can still identify our objects. Uh, yeah, that's it for 2D chromaticity histograms. And thank you so much for watching this lecture. See you next one.